So the first part of this lesson was a whole bunch of limit laws. And basically, those limit laws demonstrated that we can use direct substitution when we evaluate the limit of a function that is continuous at x equals a. But what do we do when it's not continuous there? When there is some sort of point of discontinuity, and what we want to do is like, where's that hole at? What's the y value for that particular function? What's the function approaching? And so that's what this next collection of videos is all about, is to establish some strategies for that. So let's take a look at this next example. Example 9, find the limit as x approaches 3 of x squared plus x minus 6 over x plus 3. And you can see that we have ourselves a rational function. So that rational function limit law said that we were allowed to directly substitute in x equals negative 3 as long as it doesn't make the denominator equal to 0. And you can see that it does make the denominator equal to 0. So the question is, what are we supposed to do? It all starts with direct substitution. Every bit of this, that's the very first thing that I want to do. I want to directly substitute in this negative 3 because we want to see what's happening. Is it some number over 0 or is it 0 over 0? So that's what I'm trying to determine. Is it this situation, which I would know is plus or minus infinity, it's a vertical asymptote, or is it this situation where we have ourselves some sort of hole, a point of discontinuity, and we're trying to fill that hole. We're trying to figure out where that hole is going to be. So let's directly substitute this in and see. So up top, if I take negative 3 and I square it, hey, let me show you a nifty little trick. You probably remember this from Algebra 2. You can directly substitute this in using some synthetic substitution. So I have a 1, and a negative 6. That's just the coefficients of each of these. Sure, it would have been, it's pretty easy to just substitute a negative 3 in here, but sometimes when this gets complicated, this synthetic substitution is way faster. All right, so I bring down my 1. Oops, I bring down my 1, multiply that times negative 3, I get negative 3, add it to my 1 is negative 2, multiply, I get positive 6, add it, I get 0. In other words, if I were to directly substitute negative 3 in here, I get 0, whatever the remainder is. So I get 0 on the top, I get 0 on the bottom. That is our indeterminate form. And as I said, if we get this indeterminate form, I'm expecting to see a hole, and what the limit is basically asking us is, what's the y value for that hole? Where is it located on the graph? What's the graph trying to approach at that particular point? So the strategy on this one is the exact same strategy you would have used in Algebra 2, and that is you factor. Let's see what happens when we factor this thing. So I have the limit as x approaches negative 3. And on the top, let's open up our parentheses. And x times x, we need to multiply up to negative 6, and we need to add up to positive 1. It's going to be a 3 and a 2. It will be a plus 3 and a minus 2, which is totally convenient because I have an x plus 3 in the bottom. And the x plus 3 is a common factor which divides out. It's equal to 1, right? As a matter of fact, let me just write this right over here. X plus 3 divided by x plus 3 is always equal to 1. Everywhere except at x is equal to negative 3. Right? Because if I stick in, let's say, for example, I stick in 7. 7 plus 3 is 10. I would have 10 divided by 10, which is 1. That works for every single value of x, except negative 3, because when I stick in negative 3 here, I'd have negative 3 plus 3, I'd have 0 divided by 0, which is our indeterminate form. Okay? So what this just did was give me an almost equivalent function. It's almost equivalent. Limit as x approaches negative 3 of x minus 2. And let's directly substitute in our negative 3, and I could do that because this is it's just a linear equation, which is an example of a polynomial. This should be equal to negative 3 minus 2, which is negative 5. So let me back this up and let's take a look at the graphs. Let's look at the graphs of each of these functions. Like for example, I'm going to plug this one in Desmos, and then I'm going to plug this one in Desmos. I'm just going to see what happens here. So let's call up our graphing calculator. And of course, I am not going to remember what those functions are, so I need to side-by-side this, and I am going to go with a y equaling this rational function. Those are secret answers, I need to hide them. And then on the top, I need some parentheses. It is x squared plus x minus 6. X squared plus x minus 6. That looks good. Arrow out of that thing, and then divide it, open up parentheses again, x plus 3. And then hit enter. Okay, so you can see it graphed over there in red, tiny. I'm going to full screen this in a minute. So the next one is x minus 2. So I think I got that memorized. I can go ahead and graph that. Okay, so you can see that it's a line. Why did it turn out to be a line? Well, let's see. Let's graph the next one as y is equal to x minus 2. What just happened? These two functions, the red one, the rational function, and the linear function in blue, they're exactly the same. They're the exact same function everywhere except for at the hole, and that hole occurred at -3. And basically what we did was we found a function, and that's the blue one, the linear one, that filled the hole for us. And that's the goal with these kind of questions. And that brings to mind a particular function theorem here. And the title of this theorem is Functions That Agree at All But One Point, which is essentially what we just found. So let's break this theorem up into its little parts so that we can understand what the language is telling us. Let a be a real number, and let f of x be equal to g of x for all x not equal to a in an open interval containing a. What? Well, this language we're going to see quite a bit throughout the year. Open interval containing a. But before we do that, let's examine this first part, where we have f of x being equal to g of x everywhere, or over an open interval, everywhere except for at x is equal to a. And this is exactly what we just did. We found this function, which was x minus 2, which was exactly equal to the rational function everywhere except for where that hole was. Our linear function basically just filled that hole for us, and that's what this is saying. It does say in an open interval containing a. Remember, open intervals are the ones that don't contain the endpoints. And an open interval that contains our a value, our hole basically, could be something like from -5 to +5. But really, for this one, it's from -infinity to +infinity, because those two graphs are identical everywhere except for at the hole. Let's look at the second part there. If the limit of g of x as x approaches a exists, then the limit of f of x also exists. So I'm going to pause right there. So we just found ourselves an equivalent function, hopefully a simpler function, the one that is supposed to fill the hole for us everywhere except for at x is equal to a. If this limit exists, the one for g of x exists, then so does the one for f of x. And then the follow-up to that is not only do they exist, but they're equal to the exact same number. The limit as x approaches a of f of x is equal to the limit as x approaches a of g of x. So let's break this thing down into that example that we just looked at. So the first part of it was that we were supposed to find a function that agreed at all but one point, right? That's the title of the function that's right there. So f of x is equal to x squared plus x minus 6, all divided by x plus 3. It's equivalent to g of x is equal to x minus 2 everywhere. That's the open interval. It's from -infinity to +infinity. They agree everywhere except at the hole at x is equal to -3. And we were able to get that thing by just canceling out a common factor. Okay, so there's the first part of that theorem. And the second part goes like this. Well, the limit of the linear function exists, so does the limit of the rational function, the one that we were trying to fill the hole. The limit of the g of x function exists, so does the one for the f of x function. But not only does both of those limits exist, but they're equal to the exact same number. And the linear one's really easy to evaluate because we can just directly substitute it in there and it equals -5. So therefore, both of the limits are equal to -5. And so that's our goal on these things, is to try to find a function that agrees with our function, that matches up with our function everywhere except for at that hole. And now I did say everywhere. Sometimes it's everywhere, as in from -infinity to +infinity, but sometimes it's just over some sort of smaller interval, and that's okay. All right, so how do I know I'm supposed to do this? What is going to indicate that I have to do this very complicated process? And that's when I get the indeterminate form 0 over 0. So when I directly substitute into my limit and I get the indeterminate form 0 over 0, I know that what my goal is to try to find an equivalent function, one that agrees everywhere except for at that hole. And I'm going to do that by, well, what did I just do? On this example, what I did is I factored. I factored and I got rid of that common factor. But that's not the only strategy. I've got tons of other strategies. And so something else might be that I want to, that's a really weird place for that thing to rotate, to rationalize the numerator. So up until this point, you're so used to rationalizing the denominator. That means that there is a square root in the denominator, and we're trying to bring it up to the numerator. This reverses that process. And then in the process of putting that square root from the top to the bottom, it often gets rid of that 0 that's in the denominator. We'll see that happen in one of these sample problems. And then another strategy might be, well, what I just have to do is I just have to expand some things out, collect some like terms, watch some things eliminate and simplify, and that often resolves our indeterminate form as well. So in the next couple of videos, we're going to see some of these strategies in play.